is in nuclear physics. It's going to be Amer, and he worked with Dr. Jones and Brendan Pratt. So thank you guys very much for all your support.
Okay, so I'm Amer, and my presentation is an overview of the standard model of physics. So what is the standard model, right? So the standard model describes the interactions of subatomic particles. All these particles have mass, charge, and spin, always. The standard model is supposed to be the fundamental particles. These are the smallest particles, but we don't know for a fact that they are. It's just we haven't seen anything smaller than them. They're made up of the quarks, leptons, and gauge bosons. And there's 3 generations of each of these particles. Or except gauge bosons, sorry. So generations of matter. The 2 sections of matter are the quarks and the leptons. They come in 3 sets of 2. So you have the up, down, the charm, strange, the top, bottom, and the electron, neutrino, etc., etc. Each generation of matter is progressively heavier. So you have the lightest and then the heaviest. But matter wants to be as light as possible. So generally it'll go from top to up, or from that set of generations. So we also have the forces and the force carriers. So here you'll see again, there's the quarks here, there's the leptons, and then these are the force carriers, and this is the scalar Higgs boson. The forces, there are 3 of them, but there's also 4 of them, and there's 4 force carriers that we know. Should have changed that. There's the electroweak, which is a combination of 2 forces. There's the electromagnetic force and the weak force. It's carried by the photon, the W plus and minus, and Z bosons. There's also the strong force, which is strong. It's carried by the gluon, and there's gravity, which is carried by the graviton, but we haven't seen the graviton, so I'm going to stay away from that. Sorry. So there's electroweak force. It's a combination of electromagnetic and weak forces that are really combined at higher energies. So the weak force acts through the release and absorption of W plus and Z, or W plus minus and Z bosons. It's the only way for quarks to change what we call flavor, and I'll get into that more later. It interacts with all half-integer spin particles, which are fermions. The second part of the electroweak force is the electromagnetic force. It interacts through the release and absorptions of photons, and we kind of see it every day when you use electricity or see a magnet, etc., etc. All charged particles interact with it. So the electroweak force works a lot with leptons. Like electrons are a kind of lepton. The leptons come in 2 classes. There's the charged particles, like the electron, the muon, and the tau, and there's the neutral particles, which couple with them. You have the electron neutrino, the tau neutrino, and the muon neutrino. They all have a half-integer spin, and they all also have mass and a lepton number. The second force is the strong force, and it interacts through the exchange of gluons. Gluons have what we call color and anticolor, and I'll get into that more later, and Suki will dive right in later. It interacts, again, only with colored particles, and quarks are a kind of colored particle, so they bind quarks together. It's the strongest force in nature, but we don't really experience it firsthand because it's so strong that it has to be screened always, except at quark level. So quarks, which are pretty important, make up all hadronic matter, which is what we're hadronic matter. They interact with the strong force through gluons, and they come in different flavors. So that's the top, bottom, charm, strange, up, down that I was talking about earlier. They all have a color charge, and their electric charge comes in thirds. And they're what we call color confined, which Suki will talk about later. So when we say color, we're not really talking about an actual color because they can't really be colored because they're so small. What we call them, though, is red, blue, green, and anti-red, blue, and green. So when you have what we call hadron, the colors have to neutralize. So in a proton, for example, you have a blue, red, and green, and that makes white. So that's what we call a neutral color. It can also be red and anti-red, or green and anti-green, which cancels out and makes also neutral. Any questions?
Why does it have to neutralize?
Because Suki will get into that more later, but I can answer it if you really want. She's going right after this.
Okay.
But I'm not sure if you mentioned this, but what is the definition of hadronic matter?
Hadronic matter is anything that's made out of quarks.